the three last area to be reached are these 2 points and this area. And as you can see, these two vents are quite well located because they correspond to punctual vents, but this area might be risky, and we might have some bubble and some dry spot and dry area on this area. That's why we made another run of investigation, and we made a slight modification in the strategy, that to say, instead of putting a vent point in this location, we decided to inject on this point. And the idea was to remove completely the risk that we had on this area. And at the end, we end up with this final strategy and this final filling. The very first stage was injection through the periphery, then injection through these two gates and this point. This is the modification we made at the third run of simulation. And we finally inject through this gate, and we end up with two final vents to be reached by the resin that are located in these two areas. And finally, we end up with a good, I would say, a good shape of the filling. So after defining this strategy, we use a simulation, and we recover all the data from the software to end up with this kind of graphic that corresponds to the injected volume versus the time, to say that will help us to follow the injection step by step. And of course, we end up with the total volume to be injected and also the injection time, the duration. So, as I show you in this first stage of the use of simulation, we have defined the complete strategy and the detailed strategy to be implemented to end up with a good filling of the parts. And the main point is to avoid all the risky area. And also, we end up with some very important points that correspond to injection time and total volume to be injected to fill the part. I will now explain you how we use the simulation to make the mold design. So directly coming from the simulation, we can end up with such a document that in fact explains and details the position of the injection point, and we will be able to transfer this document directly to the subcontractor in charge of the mold manufacturing. So this is for injection point. This is for the secondary injection gates, and we have exactly the same document for the position of the vent. This point is a key element in simulation because the more complicated the part is, the more complicated the mold will be, and it's very important to transfer the information directly coming from the simulation to the subcontractor to end up with a good positioning of technical points when we make the mold. Let's jump to the third item of the presentation. And so we use, as I explained you, we use the simulation to define the strategy, to design the mold, but we also use the simulation to secure the process. And more, this is a very important point because parts are getting more and more complicated, and the materials are very expensive. I'm just thinking to, for example, aeronautic parts, and that's why it's very important to secure step by step the process to avoid wasting material, time, and so on. So in this case study, we end up with such an injection report that corresponds to a kind of roadmap of the injection, and this document will help all the manufacturing department and the prototype department to produce the first part securely, taking into account all the elements that will occur during all the injection time. So to say we have a document in which one we have the corresponding time of the corresponding time, also the corresponding events to be reached, and the injected volume. To say we can follow the injection using the information from the injection machine, that are the weight or the volume already injected, the injection time, and we can check on the mold the good vent to be reached at the good time. And for this part, the very first prototype was successful because we spent a lot of time in the simulation and also to implement a good injection strategy. So as I explained, we save a lot of time in the prototype manufacturing, and we end up with a good result. And the difference between the real injection time and the predicted injected time is around 10%, because you can see here that the prediction, the simulation was 70 minutes, and we inject the total volume that were something like 300 liters in 63 minutes. So a variation between simulation and reality of 10%. This is what we can expect in RTM simulation using PAM-RTM. So our strategy is to implement process and to use the simulation. I would say to use the maximum of information coming from simulation. So we use simulation to define the injection strategy, also to define the design of the mold. This will help for the cost prediction, and we can also use, and we use daily, simulation to secure the process, to end up with roadmap during the injection. So in fact, I present you this case study that was on the inner liner part for azimuth yacht, but in PP we use daily such simulation in aeronautic, aerospace, and many other applications.
Thank you very much, Jérôme, for this very interesting presentation. So if you want to learn more, you can visit the PPE's website, www.ppe.asso.fr, or contact directly Mr. Jérôme Raynal, j.raynal@ppe.asso.fr. And you can also visit our website at www.esi-group.com, or send an email to info@esi-group.com to learn more about the composite simulation suite. So thank you very much again, and have a nice day. Goodbye.
Goodbye.